Welcome to Section 5, Convolutional Neural Networks, CNNs, and Computer Vision. In this section, we're going to take a look at deep neural networks and how they work, and specifically how convolutional networks work. We're going to use what we learned to build a flower species classifier using Tensorflow, and we're going to talk about semantic image segmentation, so that is segmenting an image into parts and classes, and we're going to be building a flower segmentation using TensorFlow as well. So welcome to Deep Neural Networks and Convolutional Neural Networks. In this video, we're going to talk about how neural networks work, how we train them with backpropagation, how they're learned with stochastic gradient descent, and specifically we're going to dive into the mechanics of convolutional neural networks and why they're good for images. So first, to cover some neural network basics, on the right is a very simple neural network. We have inputs, we have weights, we sum these weights, and we apply a non-linearity. So the output of a neural network is called a forward pass. And the output of this would be the sum of the inputs times the weights plus a bias with some nonlinearity applied to that output. This nonlinearity can be something like a sigmoid function, or it could be something like a ReLU function, which is more popular now. The important thing with nonlinearity is it allows us to model nonlinear data. So we saw this previously with things like SVMs. The power of nonlinearity gives you a much more powerful classifier. So to go from this diagram to a deep neural network, we just need to add some more nodes, as well as add some more layers. So the middle layer is called a hidden layer, and we can have as many hidden layers as we want. So when it comes to training these neural networks, an important thing is something called stochastic gradient descent. So the way stochastic gradient descent works is that we have some parameters that we want to learn, the weights of our network. We're going to call these theta. And we're going to, for n epochs, for the amount of training we want to do, for each training example, we're going to compute the loss gradient, which is the difference of what our output was versus what we wanted to output. And there's a gradient associated with that. And then we can update our parameters based on that gradient, which gives us the direction we need to move our parameters to better classify the data. So to talk a little bit about this gradient, this dj of theta d theta. Remember, j of theta is our loss function, so we want to see the gradient of our loss with respect to our parameters. And the way we do this with deep neural networks is that we apply the chain rule. So in order to get the gradient of the loss when it comes to the theta, we need to look at how it changes with respect to weight 2 in this case. So we apply the chain rule here with dj of theta dw2, which gets us dj of theta d output 0 times d output over d weight 2. So moving onward to convolutional neural networks. Convolutional neural networks work in a similar fashion, but instead of just having feed-forward layers, we have something called convolution layers. And this is kind of an example of a very typical convolutional network you might see. And there's kind of a pattern. There is a convolution, a nonlinearity, a pooling event, and then you repeat this. So the maps get smaller, but your feature maps get more and more. Specifically, the convolution operation works by applying a kernel to each pixel to produce some output map. And to apply this kernel, we take the dot product of the kernel with the receptive field of the input. So you can see on the diagram to the right, we have an image and we have a kernel that we're applying to it. And the receptive field is this grid of 9 different pixels that we're associating. So in animation, we go through each of these and we produce an output by applying the kernel to the input. And we convolve this across the image. So here it's taking the dot product, and that's how you get the specific output. And once you get that dot product, you move on to the next, and you move the receptive field over, and you get the whole output again. With convolutional pooling, what we want to do is reduce the size of our map. So the way a max pooling operation, in this case, would work is we have some features here, and we want to reduce it down to a 4x4 from a, in this case, it's a 4x4, we want to reduce it to a 2x2. What we can do is we can take the max of each grid here and just say that that is our new grid. So this reduces our map down, and this is important to reduce the feature map size so we can learn higher level features and then eventually make our final prediction. Deep convolutional neural networks follow this standard routine so that we can reduce the size of our feature maps, increase the number of our features, and this gets us a hierarchical understanding of our input so that we can produce an output.